I want to introduce my husband. You've listened to him talk now for almost 6 years, and we haven't had him give a lecture himself. And he used to do that pretty frequently as when we were both at Jefferson Lab. So he started out his physics career at 10 years old when he saw Sputnik and decided he was going to be a physicist. Got himself to MIT where they kicked him out after he finished all 3 degrees and there wasn't anything else they could teach him. And he went straight to Princeton Plasma Physics Lab. That's where the fusion part comes in for this talk. Spent 15 years there, went on to a nuclear physics lab where he was the technology officer and I was the communications director. And then he was stolen by the American Institute of Physics, where he was a director of the organization, the CEO, and he finished up there in 2007. Since then, he's been here in Lewis, and he now spends most of his time creating and teaching woodcut, white line woodcut printing, as well as lecturing about the history of science and art, and also helping his bedridden wife who just had her ankle replaced. So here's my exhausted husband to tell you about fusion, which is an interesting topic that's getting pretty hot. And I hope in the end you have a message about what your investments ought to be.
It's a pleasure to be on this side of the screen for Science and Society. I've enjoyed working with Linda and Colin, finding interesting speakers and interesting topics. This one I thought was relevant for this particular time because of a number of things that you've probably seen in the news. Number one, a lot of discussions about the fact that we may not have enough electric power when we start building new data centers, especially for the AI complex. And the second series of articles, headlines you may have seen, are about a plethora of startup companies that are proposing to bring fusion power on in the grid within the next decade. And that'll be the topic of this particular hour. Will we ever have fusion power able to generate our electricity? And before I answer that question, I thought it'd be useful to back up and remind people where we get our current electricity you're using right now to power your screen. And so let's answer that question first. And we really have to thank these two guys. Okay. You know them very well, Tom Edison and George Westinghouse. They had an incredible part to do with making the modern electrified world. Um, I enjoy reading about both gentlemen. I'm a little favored with the one on the list, Tom Edison, because of the fact that you all know he invented the first practical incandescent lamp in 1879. But I want to remind you, or tell you if you didn't know, that what he did in 3 years to basically invent an industry that did not exist, which was electric power generation and distribution. And in the course of 3 years, from 1879 to 1882, he built a power station in Pearl Street, down by Wall Street, with steam-powered dynamos. And I'll tell you about dynamos in a minute, but it's basically a generator. And he had to go from making a light bulb as an experimental device in his lab in New Jersey to being able to produce them in quantity. And then he had to invent everything else you need to connect the source of electricity to your light bulb. That included 14 miles of underground cabling. Electric cable didn't exist then. That had to be invented. All sorts of other things like switches, fuses, power meters, lamp holders. None of that existed. And in 3 years, he did all of that. And remarkably, he financed that himself in the beginning. In a little later on, J.P. Morgan realized that this is going to be as valuable as railroads, so he started investing in it. And the most other remarkable thing about this 3-year venture is that he competed against the gas companies. Now, the gas companies wanted to provide light in your house, and Tammany Hall was in the pockets of the gas companies and vice versa. So all of that happened in 3 years. And this is a model of his Pearl Street power station. It no longer exists. This model you can see in the Edison National Historic Society in West Orange. Now, it used a dynamo. Well, what's a dynamo? You know what an electric motor is, okay? Electric motor and a dynamo or generator are just their inverse um, inventions of themselves. Okay, electric motor, you put electricity in a coil and it moves the armature and you get motion. A dynamo or a generator, you turn the armature somehow with a steam-powered turbine or a variety of other things, and you get electric power out. Um, Westinghouse, of course, was a master at this. This is a power station that was built underneath Niagara Falls in 1895, and it remarkably operated until 1931. Uh, and of course, you know this one. Um, why is my slides not working here? Uh, One of the largest hydroelectric plants ever built um, on the Hoover Dam. This is built in the middle of the Depression, put a lot of people to work, and it is still operating. Now, how much power do we use in the United States? We use about 4 terawatt hours. Okay, your your home. If you look at your electric bill, you use typically about 800 kilowatt hours. If you forgot what a watt isn't a much power. Okay, it's 1 volt times 1 ampere current. You have 15 ampere plugs in your house. If you typically had a 100-watt light bulb, it used 100 watts. In the prior to the invention of LEDs, and you might ask, why did this curve flatten out over the last 20 years? It's basically because we started replacing incandescent lights, which were only about 10% efficient, with LED lights, which are about 90% efficient. And then we also got much more efficient home appliances. And so electric power really sort of flattened out over the last 20 years. And this only goes to 223. There's a bit of an upturn. And where did we get this electricity? Here's a chart plotting our various sources of electricity over the last 70 years. You can see we started out with a lot of bit of coal. Let me go back. Natural gas, hydroelectric power, the renewables are hydro, solar, and wind. And remarkably, over the last year, we have started to make as much power with renewables as we have with coal. And if I show you that a little better over the last 20 years, you see this very flat use of power along here. And you see this remarkable takeover of renewables. You also see a flat line here. Nuclear power has been flat with about 20% of our energy use over this time and the prior years to that. So we're here in Delaware. Not far from here was a very large coal plant that was put into operation in the 70s and 80s. It generated a couple hundred megawatts of coal power. Uh, Coal plants are dirty. This particular plant would produce 80,000 tons of fly ash. That's nasty stuff. That's what's left over when you burn coal, and that had to be deposited somewhere. It was deposited out on a fake island called Burton Island, which is really a Superfund site because this ash contains lots of nasty things like heavy metals. So fortunately, this plant was just finally shut down in February of this year. Getting away from the problems with burning oil or coal um, are the renewables, solar and wind. And as you saw, it's about 20% of our power needs averaged over the country. And the reason it's that high is I don't want you to get bothered by how complicated this chart is. It's just to show you that from 2010 till a couple of years ago, the cost of providing 1 watt of electricity from a solar power has gone from $6 to $1. And the cost of producing power from a wind turbine has dropped about the same amount, about 70, 80% over the last 20 years, which is why they're an important part of our generation. Now, you probably didn't think we used a lot of wind power. We actually use, there's only one country that generates more wind power than we do, and that's China, considerably more. But you see, we're well on the top of a list of countries that you thought generated a lot of power by wind turbines. If you've been in Europe, you see them all over the fields in Germany and Netherlands and Denmark. But if you compare by country, you can see, in fact, that Denmark generates over half its power by wind power, whereas we're only in the 10% range with wind and another 10% with solar. But it's a viable power source. What's the other power source where we get about 20% of our power from? Nuclear power. This is the Watts Bar nuclear plant in Tennessee. It's the last nuclear plant that was completed in the US. It went online in 2016. We have about 50 nuclear power plants um, in operation in this country, providing that 20% of our power. Now, I've just rushed through how we generate our power now, basically nuclear power, solar, wind, and coal or oil-fired steam generators. Um, we're planning as part of the Science and Society series over the spring to present a very nice program that is being put together by a research associate at our nearby University of Delaware campus here in Lewis. Catherine Leinhardt is research associate there, and she's going to be putting on a nice program for us, talking about where the state of Delaware will be getting the power it needs over the next 10, 20 years. Of course, the problem with nuclear power, you all know it. There have been some very horrific accidents, starting with 3 Mile Island in 1974. Actually, no one was really hurt by that accident, but with Chernobyl and Fukushima, a lot of people were hurt. Nuclear power plants are expensive to build, they're expensive to operate because you have to have redundant safety systems. We have, where I'm standing now, right along the Delaware River. If you go up the river a little bit and look across the river to New Jersey, you'll see the fourth largest nuclear power complex in the country. In Salem County, the three reactors on the right here are the Salem nuclear plants, they were constructed in the 70s and the 80s, been operational ever since. Hope Creek was constructed in the 80s to add to that. And these four plants generate about 4 gigawatts. That's 4 billion watts of power for the state of New Jersey, supplying about 45% of the power for the state of New Jersey. So, how does nuclear fission that powers these nuclear plants work? It exists, okay? We'll talk about fusion in a little while because it's nuclear power for the future. So, how does fission work? Well, it was discovered in the late 30s by Hans Strafman uh, in Germany in 1938. Um, and they didn't quite figure out what was going on, that uranium seemed to be spontaneously decaying into two smaller elements. Here it's shown breaking up into krypton and barium. And it was later explained that this was nuclear fission, the large atom uranium breaking apart. And when it breaks apart, it turns out there's missing energy. And that missing energy, that missing mass, supposedly, missing mass, is turned into energy through a very famous equation you all know from t-shirts and coffee cups. It's Einstein's E equal mc squared. So a tiny little bit of mass multiplied by the speed of light squared. If you have a little bit of missing mass, you get a lot of energy. Um, the amount of power that can generate from a kilogram of the isotope of uranium, which is one form of uranium that is fissionable, is equal to the amount of energy you can get from about 1 million gallons of fuel oil. So it's a lot of energy. And of course, the excitement about the discovery of nuclear fission led to all the intrigue of, of whether you could also make a bomb out of it and the Manhattan Project in the war. After the war, there was discussions of how you could have a controlled reaction between uranium and just have the reactions go at some sustainable rate, generate heat. That heat can be used to generate steam, and then you have a power plant. And the first such power plant was designed in 1951 and became operational in Idaho. It's called EBR-1, Experimental Reactor 1. It didn't generate a lot of electricity, but it showed that you could use uranium to make a controlled fission reaction, and you could control the heat and use that to generate power. Well, how do you do that? Well, here's a cartoon inside of one of those plants that's across the river from us. The uranium is stored in a pressure vessel, and it has something very important called control rods. And with the control rods inserted, they absorb neutrons, and the uranium doesn't go into a full uncontrolled chain reaction. And as you pull out the control rods, there's more of a chain reaction, there's more fission of uranium, there's more heat generated, and you have to take that heat out by running cooling water through. And you take that hot water and you make steam and you drive a turbine that drives a generator, and you have power you can sell. You also have a lot of waste heat, which is why you saw in that picture of the Hope Creek plant, there was a huge cooling tower to take out the waste heat. On the original Salem plants, they did not have cooling towers. They still don't. And they take in a lot of Delaware River water to cool the plant. And that water goes right back in the Delaware. And that's been a 50-year problem with fish kills. So there are problems with nuclear fission all around because of the safety issues, which led to the famous um, accidents, but there's a chance, and I think a very good chance, that there'll be a rebirth in the use of nuclear fission. One, because it works. Two, we've learned how to make them smaller so that they don't need expensive cooling systems to maintain their safety. And you'll hear about that in the talk that Catherine Leinhardt will be putting together later next spring on what these small modular reactors might do for the continued use of nuclear power uh, plants based on fission. Well, what is fusion, nuclear fusion? It's the other nuclear process that exists in the universe. It's lucky that it exists in the universe because I'll tell you in a moment where we get most of our power, all of in the universe is from fusion. But I have to interrupt you with a little chemistry lesson. Okay. Sorry about that. But over on the left is normal hydrogen. You remember from grade school, it had one proton and one electron. Electron, the electron is negative, the proton's positive, and so the atom is neutral. That's nice that it's not charged. But there are two other forms called isotopes of hydrogen. One exists naturally. It has an extra neutron, so it doesn't change the charge balance. It's still neutral. And about one of every 6,000 water molecules in the ocean or anywhere else in a glass of water you're drinking has a deuterium atom in it. And you don't notice it. In fact, if all of the water in a glass of water were deuterated water, it wouldn't bother you because chemically it's the same as normal hydrogen. Well, there's a rare form, a rare isotope form of hydrogen that has two extra neutrons. Again, the charge is the same. But this is a radioactive element, which means it's not stable and it decays. And it decays in about something called the half-life, when half of it is gone, in about 12 years by emitting a fast electron. You probably don't know tritium because it's sort of a waste product of the nuclear power reactors in Canada that run with deuterium. And it can be made other ways. That's where most of it comes from. And its most common application is to put small amounts of tritium in a glass capsule and coat the glass with a phosphor. And that's what the modern exit sign is that you see in many places because the tritium will last 12 years. You don't need a battery to have a small amount of light. But when we're going to talk about fusion, it's these two forms of hydrogen that are most important. So here's the most probable nuclear fusion reaction. It is a reaction that takes deuterium with one neutron and tritium with two neutrons and knocks them together. And if you knock them together with sufficient energy, sufficient speed, sufficient temperature, they're all measures of the same thing, they will fuse. And you get two neutrons, two protons. It's now the element helium. Okay, you know helium. Um, but you also kick out a spare neutron. And I apologize for these units. These are physicist units here. But this is a lot of energy coming from this reaction. Again, if you took a kilogram of deuterated and tritiated hydrogen and made this reaction go, it would generate as much energy as 1,000,000 kilograms of of oil or gas. So it's a very efficient way to generate energy if, and this is a big if you could make it go. Well, we know it works. Trouble is, it's the dominant source of stars. That it's fusion of hydrogen in stars that makes up their energy. Well, that's too big. We can't bottle a star and put it on the planet. The first man-made demonstration of fusion was in 1952 when relatively small amounts of deuterium and tritium were made to fuse by surrounding it with a normal atomic weapon. And that led to the first hydrogen bomb and a succession of hydrogen bombs since then. Well, that's too uncontrolled release of energy. You can't imagine designing a power plant by by dropping hydrogen bombs. So we knew it worked, and the problem was reduced to how can we make fusion happen in a laboratory setting much smaller than a star, and at a much more controlled time scale than a bomb. And it picked up the wording, how do we develop controlled nuclear fusion? And this has been a 70-year venture. Linda, your moderator, mentioned that I spent my first 15 years working at one of the country's and the world's premier fusion labs, Princeton Plaza Physics Lab. Several of my colleagues are on tonight. Um, it is a remarkable scientific venture that occurred over this 70 years. I'm going to just quickly work you through that. But I remind you, the sun, it works because it's fusion of hydrogen to form helium and all that extra mass, the missing mass from the fusion reaction is turned into energy by Einstein's equation, about 600 million tons of hydrogen per second. Okay? That sounds like a lot. It is a lot, but the sun's a big place. It happens only in the sun's core where the temperature is a mild 15 million degrees centigrade. So you're now getting a bit of an inkling of why fusion on a laboratory scale or an Earth-sized power plant is difficult. How do you take these two forms of hydrogen and heat it up to tens or hundreds of millions of degrees? It's easy in a star. It's easy very quickly in a hydrogen bomb. What happens when the sun burns up all of its hydrogen through fusion? Well, it'll burn out, and but you don't have to worry about that. We've got about 5 billion years of fuel left, so don't make that one of your nightly worries. So the other example of hydrogen fusion working is in the H-bombs, as I mentioned. And here it involved the easiest fusion reaction, one I told you about, the deuterium form of hydrogen, the tritium form of hydrogen, making helium and a neutron. But it also, since it got very hot very quickly, it worked on two other reactions. Uh, One only needs to get about 100 million degrees, and you can get fusion to work. Thanks to stars and thanks to thermonuclear bombs, we know fusion works. So why is it so difficult to do in a laboratory scale first? Well, it happens to do with something that has been often called the holy grail of experimental nuclear fusion, the triple product. And this was first uh, really discussed quantitatively by a gentleman by the name of Lawson, British scientist. And he calculated that if you took sort of a modest density of hydrogen, I'm using scientific notation here, 10 to the 14th hydrogen atoms per cubic centimeter. 10 to the 14th, that's sort of 100 trillion, okay? Um, that density is about 100,000 times less dense than the air we're breathing right now, okay? So it isn't a lot of hydrogen. So getting the density at room temperature and room pressure is not the problem. You then have to heat that amount of gas to 100 million degrees. And you have to hold the heat for at least a second. It's called confinement time. So if you got that density, heated to that temperature for that time, that's called the triple product. And at that point, you would be making as much energy from fusion as you had to put into the reaction to heat it to that temperature. That magic condition is called energy break even, or Q equal one. We've had a 40, 50-year history of using that terminology. Well, this is the hard part. Okay. How do you heat gas to 100 million degrees? And what do you hold it in? Right? Well, I have to backtrack before I answer those questions to tell you that it's not a gas at that point. You're familiar again from grade school that of three forms of states of matter. A solid, you heat up a solid, it melts, it becomes a liquid. You heat up a liquid, it melts, it becomes a gas. Well, it turns out you can continue to heat a gas. You've got to heat to about 10,000 degrees or higher, and you'll boil off the electrons, leaving just the nuclei, the ion. And that remaining mixture of now charged particles, the electrons that boiled off and the ions that are left behind by the positive charge, that's called a plasma. Now, you've probably heard the word plasma for blood plasma. They're both they're both used. One's used in biology and medicine, and this one's used in physics. And there's plasmas all around you. You probably didn't know it. The sun and all the other stars are all plasma. So-called neon signs were originally a glass tube with neon gas, and you electrified it, and you made a low temperature plasma of the neon gas, and it gave off a red light when the plasma hit the glass tube. And I'm sure a few of you saw a few weeks ago that right here on the Delaware shore, we had some nice aurora. Those are plasma. So plasmas are around. But how do you contain a plasma? Without the plasma hitting the wall of the container and cooling off, and your game is to try to heat it, or burning a hole through the container. Well, the answer is there have been two schemes that have kept my colleagues at Princeton Plasma Physics Lab and several other labs in this country and in the world busy for 7 decades. One scheme uses very clever magnetic bottles. Turns out, remember I told you that a plasma is an ionized species, so it's got a charge. And if you have magnetic field lines, you remember seeing from a kid when you put iron filings over a magnet, it shows those lines. An ionized species will curl around the magnetic field lines. And if you're clever in designing the scheme of the magnets, perhaps you can keep the ions confined. So that's called magnetic confinement. And the second scheme is called inertial confinement. And there you don't work with a gas. You work with a small pellet of the frozen hydrogen, less than a millimeter, and you hit it with gigantic lasers to compress it to reach the same conditions that I told you, high temperature for enough period of time and a certain density for you to make more energy from the fusion than you had to put in heat to those temperatures. So those are the two schemes, magnetic confinement, magnetic bottles, and inertial confinement, big lasers. So let me show you what some of these things look like. There have been at least, I'm only going to concentrate on two of these schemes for um, magnetic confinement. One goes by the name tokamak, It sounds like a Russian word because it is a Russian word. They invented the configuration in the early 70s, and it's basically a donut um, where the plasma goes around the center of the toroid and you wrap magnets around. And you have to be very clever about the magnets because a simple toroidal field, I don't have time to explain it to you, won't confine the plasma. You have to have a more complicated field that extra magnets comprise. And a version of a magnetic confining device that actually predates the tokamak is something called stellarators. And they work with really wonking looking magnets to try to, if you can imagine the plasma wanting to be a slinky, well, then you fight slinkies with slinkies. The early studies in Princeton were started by this gentleman, Lyman Spitzer. He died in 97. He was the chair of Princeton University's Astrophysical Sciences Department through most of his time at Princeton. And as the story goes, Professor Spitzer was a very active man. He was a mountain climber. He was a skier. And I have to remind you, in the early 50s, the physics community has just come back from doing very important things for the war effort, inventing radar, inventing the atomic weapons in Manhattan. And there was an aura about physics and physicists being able to solve any problem. And Professor Spitzer, on a ski trip, thought that he could design a magnetic scheme that would confine plasmas. And this was his scheme, his star machine called a stellarator. And it was basically a twisted array of magnets, kind of like a pretzel, a figure eight. And this is a picture of his so-called Model A stellarator. And certainly, shortly after he invented this device, and it became the first work to be done at the young Princeton Plasma Physics Lab in the 50s. Um, he felt that you could go from a simple device like this, so-called Model A, to a Model B that was bigger and higher and more complicated magnetic fields, to when I first heard about work at Princeton when I was about 12 years old. They built Model C, the Model C stellarator, and that's when um, the major facilities at Princeton Plasma Physics Lab were developed. And he felt that after Model C, all the problems would be worked out, and Model D would be a prototype reactor. As you can see, as I give you the rest of the story, it didn't quite work out that way. Professor Spitzer left plasma infusion devices after founding the laboratory and being its first director, and went on to do something that you probably didn't know he was the father of. He was the father of the space telescope. He proposed in the 40s that if we could get a telescope above the atmosphere, that we would be able to see stars and galaxies much clearer without the atmospheric blanking of the light. So here's where stellarators have gone to. The world's largest stellarator is in Greifswald, Germany, on the North Sea. I have, my colleagues at Princeton, I have a good friend, Fritz Wagner, who was the director of this program. And look at these pretzel magnets that were designed around the vacuum vessel. The plasma itself is in a vacuum vessel underneath these magnets. And some of you know my daughter, Kim, who's a very good artist, and an homage to her father is that she likes to do oil paintings of famous physics devices. This is one of her oil paintings of the magnets at the the Wendelstein 7X stellarator. So the lion's share of the work towards getting fusion at Princeton and in this country was done at Princeton on the so-called tokamak fusion test reactor, TFTR. It was thought about in the late 70s. Construction began in 1982 and it ran till uh, the late 1990s. And it actually, this device and a device I'm going to tell you about very shortly, one in England, actually came close to producing the Holy Grail, the so-called Q equal one, trying to make as much energy from the reaction as you had to put in to heat the plasma. TFTR and its best discharges with deuterium and tritium, the easiest reactions to fuse, got to a Q of about 0.3. Not enough to make a power plant. You know, you need to generate more power than the power put into it. But it was a huge step in the right direction. So it's this device that was built and designed and operated at the same time, a little longer because it just shut down 2 years ago, called the Joint European Torus. It was put together by the European fusion community. And this device actually, when it ran on deuterium and tritium, uh, produced a Q of about 0.6. Again, not enough, but getting closer. So here's a complicated plot that shows you each one of these acronyms is a fusion device, a magnetically confined fusion device, going up to the ones I just showed you, JET, Joint European Torus, and TFTR, and here's a Japanese machine. But here's temperature plotted along this way, and these are the other two parameters, the density and the confinement time. And you can see that got very close to the so-called energy break-even, Q equal 1, but didn't get across the line. And I'm going to tell you about in a few minutes a machine that's still being built called the International Tokamak Engineering Reactor that will get close. Its goal is to get beyond Q equal 1 to so-called ignition conditions where you could design a reactor. This is the remarkable part of the science and the engineering that I want to emphasize to you. Okay? Even though 70 years after this exercise was begun, we haven't achieved Q equal 1 or energy break even. There was this remarkable 100,000 change in parameter.
Well, could you bring up pencil?
Somebody's got their microphone on. I think.
Oh, thanks.
Yeah. This is the original Russian tokamak T3 back in the 60s, going up to TFTR and JET, JT60. You can see that the parameter improved 100,000 times. There isn't much that has improved 100,000 times over that period. One that comes in mind is what's in your watch and in your calculator and your computer. And that's our ability to put transistors on a semiconductor chip. Going back to 1972, the 4004 Intel chip going to the Pentium at the turn of the century, you can see that the performance of computer chips doubled about every 2 years. So did the performance of fusion devices. But it stopped. The goal of the test reactor is another factor of 10 higher and a little higher for a fusion power plant. So what happened? Well, the test reactor. That started with a very famous summit between Reagan and Gorbachev in 1985. Here they are signing an agreement for joint fusion research. And that led a few years later to the international collaboration of plasma physicists all over the world to design and build the International Tokamak Experimental Reactor. The design study started around 2007. Construction activities started a little after that. It's still under construction. It's a very big machine. Remember, I showed you a picture of JET, the Joint European Torus. Here's the standard 2 meter, 2 yard high person. You can see how big JET is. And it looks even better. This is a recent photo where you can see pieces of the machine coming together. It's a monstrous machine. And I don't expect you to read this schedule, but I'm going to point out that it is not expected to have first operation of plasma till the early 30s and not until the 40s, almost to the 50s to get above the so-called Q=1 conditions. But it's being helped because there are fusion labs all over the world. I've just been talking about Princeton, but they're all over the world, and this truly is an international collaboration because it's so difficult. And until recently, there was no interest in commercializing it. The Chinese have been very active. This is a conceptual model of their fusion power plant. You can see it looks very similar to what I showed you on a fission plant in a cartoon, cooling towers, a containment vessel, generators. But how would you extract power? We go back to that same bit of chemistry. Deuterium ion, tritium ion fuses, you get helium, you get a neutron. Well, the helium is ionized, okay? It's captured in the plasma. It actually becomes the ash of the reaction. Pretty benign ash when you talk about it compared to the ash of a coal plant. But it's this neutron moving very quickly that has to be captured, and that's where the power comes from. And so here's a little cartoon that shows the hot plasma, and it comes through whatever the first wall, which is no easy thing to design. And then, remember I told you tritium doesn't occur naturally, so you have to design what's called a tritium breeding blanket that would make the tritium to keep the power plant going. Deuterium you can get from seawater. Then you got to take the heat out, and it's that heat that's used to make steam to drive the turbine. Then you got to shield all of that because there's an intense radiation and thermal load, and you don't want that to get into the magnets. Pretty complicated, right? Doesn't look simple. Well, or it doesn't look inexpensive. Is there another scheme for fusion? I mentioned it at the very beginning. It's called inertial fusion. And in just a couple of years ago, 221, at Lawrence Livermore National Laboratory, they actually achieved Q=1. And a year later, Q greater than 1. Not a very easy experiment to duplicate. It hasn't been done anywhere else in the world because it involves a very complicated small frozen pellet of deuterium and tritium in a special chamber, and you hit it with 190 lasers. It's the biggest laser complex in the world. And they've done it 5 times. From 222 to 224, actually making about twice as much energy as they had to put into it. But now, can you imagine a power plant? Here's the size of the laser bay that they've fired, about once a month. Here's their cartoon of what a power plant would look like. You have to design some way to make the pellets so that you have about 900 of them a minute, as opposed to one every couple of months, and then you have to fire the laser 900 times a minute. And after that, it looks like the other fusion plant. It's got a lithium blanket to take the heat out and heat exchanger and turbines. Doesn't sound easy, does it? Well, here's the other part of the story. Over the last 5 years, 53 companies, largely startup companies, have attracted over $10 billion of private money to bring fusion power to the market. And we're 1 year into a new administration. The realigned Department of Energy has a new Office of Fusion Energy, and they've just published its Fusion Science Technology Roadmap. And this roadmap intends to emphasize milestones not only for the Department of Energy laboratories like Princeton and Livermore, but also take advantage of these public-private partnerships. They have an idea that they want to mimic what has happened in the space community with companies like SpaceX. But there's no new science in building and designing a rocket. There is new science still 70 years later with fusion because we still haven't gotten the Q equal 1 conditions. I'll show you the names of some of these companies. Helion Energy intends to build a fusion power plant for Microsoft Data. There's a German company that's raised 113 million euros called Marvel Fusion. What a great name. Here in the US, the one company that seems to have a leg up over the others is called Commonwealth Fusion Systems. It's a spin out of my alma mater, MIT. I think they will do some great work on magnet generation, design and building, but they're proposing to build a first grid scale power plant in Chesterfield County, Virginia, to provide power to Google and Microsoft. And you can read their press release from this summer. Here's another one, TAE Technologies. They proposed to do the same thing with a different scheme. Here's the laboratory up at Devens, Massachusetts. You can see there isn't much to show yet. If you're going to have Q equal 1, first plasma next year and Q equal 1 shortly thereafter. And then you have these deals to deliver a power plant not too long after that. TAE Technologies is the different kind of scheme, but they're making the same kind of promises. And in Europe, the UK government has offered just under £500,000 to build a fusion power plant to replace this coal plant that is being decommissioned in Nottinghamshire. Well, back to my opening question. Will fusion power ever generate our electricity? My answer is very clear. Even though I've been out of this business for 35 years, I've kept in touch with my colleagues at Princeton. They're a wonderful group of people. I've learned a lot from them during my career. I believe most of them agree with this answer. There's not going to be fusion power generating our electricity anytime soon. But I have an important caveat. You saw the remarkable progress that fusion made from this 70 years of research, 70 years on magnetic confinement, 60 years on inertial confinement. It's one of the most difficult problems known to physics. If it was easy, it would have been done a long time ago. Because it's difficult and because we've made that tremendous progress I've showed you, I feel and my colleagues feel the work should continue. And especially as fuel for stronger international collaborations, not only to push fusion beyond the magic Q equal 1 break-even number, but also for the unique spin-offs that have come out of this technology. Magnets, normal magnets, superconducting magnets that are in MRI machines, high-strength materials for severe environments, the computations that have been done to tame plasmas are a very important part of what's being generated. All of that should continue in my view. So, what are my analogs for the fusion venture? I have two. One is cathedral building. Here's probably the most famous cathedral in the world, Notre Dame, recently rebuilt from its disastrous fire. Um, it was started in the 11th century, finished in the 12th century. Those people working on cathedrals never saw the cathedral finished in their lifetime, but they felt it was important to do. I will never see a working fusion reactor in my lifetime, but I think the work is important to do and continue. My other analog is on a little closer to home. It's the New York City water tunnels. There are two of them that have been in existence since the 30s, bringing beautiful Catskill water down to New York City. And you know, New York City water wins taste tests all the time. The third tunnel has been under construction for 30 years. It doesn't have a known completion date, but it's an important thing to do. They especially want to get the third tunnel done because there's some valves that are the size of these tunnel diameters that don't work on the tunnel one and number two, and they want to get tunnel three working before they can do maintenance on tunnel one and tunnel two. So we have analogs for fusion where people who are working on the projects work for longer than their lifetime. You want to read more about fusion? I have a chapter in the book that I published in 220 called How Long is the Fusion? Fusion, that's a nice short version of this talk. Longer ones are in these two books, Science, Politics, the Invention of a New Energy Source. It was published in 1982, but it's still quite relevant. And this book just published 3 years ago is quite good. And I owe a lot to my former colleagues at Princeton Pleasant Physics Laboratory for this talk. So with that, I'll entertain some questions.
So, since we're bumping right up at 6 o'clock, I put the message out there for everybody in the chat box. Anybody that wants to leave now, feel free to do so. Fred had a lot to say, as usual. I've got some questions here, Fred, that I think are relevant to our discussion in a big way. One of them is, how relevant is Lawson's criterion to current approaches to nuclear fission? I thought that one of the key things to controlling fission,
Fusion. Are you talking fusion or
fusion,
fission?
sorry, I'm talking fusion. I thought it was believed to be that fusion could be controlled in the 1960s and 70s. Is it still a key theory?
Um, Look, fusion, you got fusion reactions on every experiment that was tried. You just didn't get enough to generate more energy than you had to put in to make those fusion reactions, whether it was one or millions of them. You have to get to the point, the magic point of Q equal 1, which is energy break even, which says I got as much out of the reaction as I had to put in to get to those stellar temperatures. And that's a scientific demonstration because you can't build a power plant if you're just making enough energy to compensate for what you put into it. So you really need Q around 10 or so that you can run the plant and have power to sell. So that's why this has been so difficult. We got close to Q equal 1, but we're nowhere near Q greater than 1. Perhaps ITER, the International Tokamak Engineering Reactor, will get to it in the 40s. Now, how will these startups do that in the 30s? I think they're all smoking stuff funny. And if you're investing in any of these
Get
companies
out
take your
now.
money out.
Get out now. Tell me, this is another question I think is compare and contrast the safety aspect of nuclear versus nuclear power, fission versus fusion.
Fusion.
Yeah.
That's an excellent question. So you can see it's been so hard to get a nuclear fusion reaction to work that anything that goes wrong with the plant, the reaction will die. And so it has none of the runaway um, reaction problems that a nuclear fission plant has. If a nuclear fission plant loses its cooling power, the heat runs away and it can melt down, just as what happened at Fukushima. Okay? The uh, the other thing that's safer with fusion than fission is the fuel cycle. With fission plants, we bring in tons of uranium, especially purified uranium. And then when we've used that up, it has to be taken out and it's highly radioactive. And this country has never developed a repository to put those used fuel rods, which is why they're sitting in swimming pools around every fission plant. So here in fusion, the fuel is deuterium, which you can get from seawater, tritium you make in the plant, and the waste product is helium. So for those two reasons, that it can't have a runaway reaction and it has a very clean fuel cycle, it would sure be nice if fusion worked.
One last one. Which of the two schemes, the Tokamak versus the Stellarator, do you think these startups are thinking about using? Is it the magnetic toroidal or the laser version?
There are so many startups, they basically picked up on every scheme. I only told you about two magnetic schemes, a Stellarator and a Tokamak. There are some that have chosen tokamaks. There are some that have chosen stellarators. There are some that chosen other magnetic configurations, and there are some that have chosen laser-driven or ion-driven. They picked up the whole plethora of things that have been tried over the first 50, 60 years of this, but not running with any of the reality that the world's investment in fusion has shown you.
One more question, then I'm going to stop because everybody needs to go have some dinner. Lynn G was taught that you could dispose of fission waste by burning it in a fusion reactor. Is that possible?
Look, anytime that you have a very strong source of neutrons, you can irradiate radioactive material and change it into a less, a more desirable form. And so, yeah, that possibly uh, could be another application. There, in fact, were designs of fission plants, which are a source of neutrons, that would be specifically used to clean up nuclear fuel from other nuclear plants because it's an unsolved problem. We're just storing it. We're not doing it with it. And it's a very expensive fuel. It could be recycled if you cleaned it up.
Excellent. Well, I think we've covered most of the questions, and you covered the field very well, and I didn't have to interrupt you to correct you for something which I've been known to do. So,
He's a tough
congratulations.
moderator, folks.
Those of you who have been with us before know that you can unmute yourself now and clap for Fred if you want to, or just get off. It's one or the other. But I hope we've answered all your questions. You've got my email. So if you have more, well, you
I'll answer
almost all
them.
of you do if you're on my newsletter. Email me if you've got more questions. Fred will be happy to answer all of those
Yeah.
questions.
All right.
So we appreciate it. And a lot of his
Yay.
Princeton
Thank you,
colleagues were on,
Fred.
as was
Good
Thank you.
job.
It was
Fred.
wonderful.
Thank
Thank
you.
you,
Great talk.
Fred.
Thank you
Good,
both.
Fred.
Thank you
Great
very much.
job.
Thank you.
And Linda, good luck with your recovery.
Yeah,
Thank you. I need it.
I bet. I bet.
It's
Thank you.
bad.
Can we
Bye
see
bye,
you run to your
Diana.
crutches now?
I'm not even using those. They're there for decoration. I'm still on a walker.
Oh, you really?
Thank you. I
Yeah.
learned so much. I
Yes.
Take
learned so
care.
much.
thank
that was
you,
great.
Fred.
Thank
Thank you,
you.
Colin.
Bye
Thank you, Colin.
bye.
Thank
Bye.
you.
Here,
Good
Ruth.
night.
Bye.
Great talk.
Bye.
Each.
All right, everyone. Thank you for joining us. Have a good evening. Good night.
Good night.